and hello to you too. Now, see, if you recall, towards the end of my last class, we spawned another thread, a thread on binomial theorem, a subcase of multinomial theorem, and so on and so forth. All right, and we established the result using combinatorics, right? Now we'll go ab initio with the same thing, independent treatment of the whole thing, and examine properties and applications of the same. All right. To begin with, let me start with the very simple expression 1 plus x whole to the power n, where n is a natural number, What does it actually mean? It means 1 plus x into 1 plus x into 1 plus x, how many times? N times. N times. When I write this, am I writing an equation or am I writing an identity? This is an identity. If I write 1 plus x whole squared is 1 plus x into 1 plus x, then this statement is indiscriminately true for all values of x and therefore is deemed an identity and not an equation. It's an identity, right? If I write 1 plus x whole squared is 1 plus x into 1 plus x, it's an identity, not an equation. You can plug in any value of x on the left hand side and the same value of x on the right hand side, and you have an identity in place. Now, when I multiply this out, right, do you realize that x into x into x into x into x, x power n, the highest power of x is n. The highest power of x is n. And then 1 into 1 into 1 into 1, that is x power 0. The lowest power of x is 0. That means when I expand this, I'll have powers of x starting from 0 all the way to n. Powers of x starting from 0 all the way to n. That would be the spectrum of terms made available when I expand this, when I multiply all the n terms in this, right? Which means the terms would be of the kind, let's say a term with x power 0 is a naught, right? Then a term with x power 1 is a1. This is the coefficient of x power 1. Coefficient of x power 2, let me call it a2, x squared. Coefficient of x power 3, let me call it a3, x cubed. Coefficient of x power n, let me call it an, which is xn. Yes or no? These coefficients as of now are not known to us, and to begin with, these coefficients a0, a1, a2, a3, an would be referred to as undetermined coefficients. Right now these coefficients a0, a1, an will be referred to as the undetermined coefficients. They are the undetermined coefficients, right? We need to find the values of a0, a1, a2, a3, an. Clear? Now, even before we venture into finding these values, some things that one can very readily see, even if one didn't know the values of a0, a1, a2, an, is the following. Say, since this is identically equal to this, then the two expressions are equal for all values of x, right? Let me plug in x equal to 1 on both sides. Let me plug in x equal to 1 on both sides. Then I end up getting a0 plus a1 plus a2 plus an, right? a0 plus a1 plus a2 plus a3 plus an equals 1 plus 1, that is 2 to the power n. That means the sum of these coefficients will always be 2 to the power n. The sum of these coefficients will always be 2 to the power n. Now, plug in x equal to minus 1 on both sides. Plug in x equal to minus 1 on both sides. Then you have a0 minus a1 plus a2 minus a3 plus a4 and so on and so forth equal to 0. If you plug in x equal to minus 1 on both sides, that means a0 minus a1 plus a2 minus a3 and so on and so forth, that's equal to 0. That's equal to 0. Right? Which means this gives me a0 plus a2 plus a4 etc. equal to a1 plus a3 plus a5 etc. Right? Which means these are the sum of the even coefficients 0, 2, 4 etc. 1, 3, 5, this is the sum of the odd coefficients. Sum of the even coefficients will be equal to sum of the odd coefficients, right? Isn't it? Now, if A equals B, then each will be half their sum. If A equals B, then each will be half their sum, right? So if this equals this, then each will be half this plus this. Is it not? That means each will be equal to half of a0 plus a1 plus a2 plus an, right? Is it not? But a0 plus a1 plus a2 plus an is actually 2 to the power n. So 2 to the power n divided by 2, that makes it 2 to the power n minus 1. That means sum of the even coefficients is sum of the odd coefficients. Each will be equal to 2 to the power n minus 1. Each will be equal to 2 to the power n minus 1. What did you not understand? If 3 equal to 3, each is equal to half of 3 plus 3 are. Isn't it? If this is A and if this is B, then each will be half of a0 plus a2 plus a4 plus a1 plus a3 plus a5, which rewritten is a0 plus a1 plus a2 plus a3 plus a5. But a0 plus a1 plus a2 plus an is actually 2 to the power n divided by 2, that makes it 2 to the power n minus 1. That means sum of even coefficients is sum of odd coefficients and each will be 2 to the power n minus 1. Does that sound okay or not? Right? Now, in this, replace x by 1 by x. This is an identity and you can play around with it very frivolously, right? Replace x by 1 by x. When you replace x by 1 by x, what do you get? 1 plus 1 by x whole to the power n is a0 plus a1 by x plus a2 by x squared plus a3 by x plus a4 by x plus a5 by x plus a6 by x plus a7 by x plus a8 by x plus a9 by x plus a10 by x plus a11 by x plus a12 by x plus a13 by x plus a14 by x plus a15 by x plus a16 by x plus a17 by x plus a18 by x plus a19 by x plus a20 by x plus a21 by x plus a22 by x plus a23 by x plus a24 by x plus a25 by x plus a26 by x plus a27 by x plus a28 by x plus a29 by x plus a30 by x plus a31 by x plus a32 by x plus a33 by x plus a34 by x plus a35 by x plus a36 by x plus a37 by x plus a38 by x plus a39 by x plus a40 by x plus a41 by x plus a42 by x plus a43 by x plus a44 by x plus a45 by x plus a46 by x plus a47 by x plus a48 by x plus a49 by x plus a50 by x plus a51 by x plus a52 by x plus a53 by x plus a54 by x plus a55 by x plus a56 by x plus a57 by x plus a58 by x plus a59 by x plus a60 by x plus a61 by x plus a62 by x plus a63 by x plus a64 by x a3 by x cubed an minus 1 by x power n minus 1 an by x power n. Yes or no? Is that not what you get? Right? Now multiply throughout by x power n. Multiply throughout by x power n. If I multiply throughout by x power n, then I get again 1 plus x power n equals a naught x power n plus a1 x power n minus 1 plus a2 x power n minus 2 plus an is what I get. Is it not? On multiplying throughout by x power n, this is what I get. Hey, but 1 plus x power n is also equal to this. And 1 plus x power n turns out to be this. So let me equate this expression to this expression, because both are equal to 1 plus x power n, right? So this is also equal to a naught plus a1x plus a2x squared plus a3x cubed plus anx power n. Yes or no? Right? Isn't it? That means this polynomial is identical to this polynomial. This polynomial is identical to this polynomial. And if two polynomials are identical, then coefficient of x power London in one polynomial will be equal to coefficient of x power London in the other polynomial. Coefficient of x power Hong Kong in one polynomial will be equal to coefficient of x power Hong Kong in the other polynomial. That means we can equate coefficient of equal powers of x on both sides, right? So if this polynomial identical to this polynomial, what's the coefficient of x power n here? A naught. What's the coefficient of x power n here? An. And therefore a naught must be equal to an, right? A naught must be equal to an. What's the coefficient of x power n minus 1 here? A1. What would be the coefficient of x power n minus 1 here? An minus 1, right? The term just before this must be an minus 1, which is the coefficient of x power n minus 1 on the right hand side. Nahi kya? Huh? So coefficient of x power minus 1 on this side is a1 must be equal to coefficient of x power n minus 1 on this side, which is a n minus 1, isn't it? The term prior to this, a n minus 1 x power n minus 1 plus a n x power n. Coefficient of x power n minus 1 on the right hand side is a n minus 1. Similarly, coefficient of x power n minus 2 is a2 here, and that must be equal to coefficient of x power n minus 2. The term prior to this would be a n minus 2. And similarly, if you keep going this way, you get ar equal to a n minus r. Right? Where r can assume values like 0, 1, 2, 3 up to n. These are the permissible values of r. Meaning what? If this is the expansion of this, then coefficient, yes, coefficient of terms equidistant from beginning and end must be the same, provided you are writing in either an ascending order or a descending order. If you are maintaining the same order, then coefficient of terms equidistant from beginning and end must be the same. Got me? In fact, a similar thing could be applied to many other expressions. For example, you know, just to take a little detour from this, say I had 1 plus x square whole to power n, right? Now do you realize this is 1 plus x squared into 1 plus x squared into 1 plus x squared, how many times? N times. That means the highest power of x would be, take the last term, x square into x squared into x squared into x squared n times, that is x to power 2n. The smallest power of x would be 1 into 1 into 1, that is x power 0. Yes or no? That means if you had to expand this, then would you not expect something like this to happen? You would expect, let's say, a naught as the coefficient of x power 0, then a1 as the coefficient of x power 1, then a2 as the coefficient of x power 2, then an x power n, then a2n x power 2n. Is this not what you expect? Right? Say a2n minus 1 x power 2n minus 1, a2n x power 2n, right? In this case also, in a situation of this kind also, a very similar property will emerge. One thing, if you put x, if someone says, even if you didn't know the actual values of a naught, a1, a2, a3, an, etc., you can find the sum of a naught, a1, a2, a3, an, a2n. How? By plugging in x equal to 1 on both sides. You know what I'm saying? What? I'm saying these are unknown numbers, but I say this is an identity, and you can still find the values of a naught plus a1 plus a2 plus a2n. How? Put x equal to 1 on both sides. So if you plug in x equal to 1 on both sides, then you get 3 to the power n is a naught plus a1 plus a2 plus a3 plus a2n. Some of these coefficients would be 3 to the power n, right? Let's see how we could see. What I really want to do to you is to train you very generally on this, rather than get very specific about specific formulas results. Get a very general training on this, so that you have the flexibility and the leverage to play around with things and arrive at your own concoctions. Okay, can I wipe this off? Right now, notice another beautiful thing that can happen here with this kind of an identity. Can I wipe this off? Right? These are some very common practices and will come in very handy, very useful. All right. Let me replace x by 1 by x. Let me replace x by 1 by x. Once again. So 1 plus 1 by x plus 1 by x squared whole to the power n. Right? That's going to give you a naught plus a1 by x plus a2 by x squared plus a3 by x cubed right? Multiply now by x to power 2n both sides. See, if I took the LCM of this, what would it be? It will still be 1 plus x square by x squared. Right? And raised to the power n, that x square would become x power 2n. And then uniformly multiplying with x power 2n on both sides, you end up getting 1 plus x square whole to power n. That's equal to a naught x power 2n plus a1 x power 2n minus 1 plus a2 x power 2n minus 2 plus a2n. Is this not what you get? Hey, but 1 plus x square is identically equal to this and is also identically equal to this. Right? Therefore, 1 must be identical to 2. 1 must be identical to 2, yes or no? Right? And therefore, if 1 is rendered identical to 2, this expression rendered identical to this expression, then coefficient of x power London on one side must be equal to coefficient of x power London on the other side, right? What's the coefficient of x power 2n on this side? A naught. What's the coefficient of x power 2n on this side? A2n. A naught is A2n. Coefficient of x power 2n minus 1 on this side is A1. Coefficient of x power 2n minus 1 is A2n minus 1. And going this way, in a very general sense, you end up getting AR equal to A2n minus R. Right? Which again means, for something as symmetric as this, coefficients of terms equidistant from the beginning and end ought to be the same. Right? Something like this. Can I wipe this off?
If the coefficients of x in the left hand side is not 1, then the same result will be there. If the coefficients of x and x square is not 1,
No.
it's something else. So still this will be there, that first term's coefficient is equal to the last term's coefficient.
No. No. That's not going to be the case. It'll lose its basic virginity if you read that. Coming back to this then. Coming back to this. What transpired here was 1 plus x power n is a naught plus a1x plus a2x squared plus a3x cubed plus arx power r anx power n, right? Some basic properties that we arrived at. One was a naught plus a1 plus a2 plus an turned out to be 2 to power n, and a naught plus a2 plus a4 etc. will be equal to a1 plus a3 plus a5. Each will be 2 to power n minus 1, right? But about time we also found the actual values of these coefficients undetermined, but let's be determined enough to find them, right? What we do is, this being an identity makes life easy for us, because then we enjoy the luxury of plugging in any value of x that we deem fit on both sides, so as to conveniently obtain the values of a naught, a1, a2, etc., right? Put x equal to 0 on both sides to begin with. Nobody stops you from doing that, right? Putting x equal to 0 on both sides, you get 1 equal to a naught. Ah, good. We know a naught now, right? Now that we know a naught, let's get worldly wise. Let's throw a naught out and then seek to find a1. Let's seek to find a1, right? Hey, if you differentiate an identity, you still get an identity. X plus 1 whole squared is x squared plus 2x plus 1. And if you differentiate both sides, 2 into x plus 1 would be 2x plus 2. Differentiating an identity would give you yet another identity. Let's differentiate both sides with respect to x. So when I differentiate both sides with respect to x, then I get n into 1 plus x power n minus 1 equals a1 plus 2a2x plus 3a3x squared plus rar x power r minus 1 nan x power n minus 1 is what I get, right? Put x equal to 0 again. Put x equal to 0 again in this newly found identity, right? Plug in x equal to 0 again and you end up getting n on this side, right? That's equal to a1 because all of the terms go into oblivion, right? And a naught, which is 1, is actually nc0, isn't it? a1, which is n, is actually nc1, nc1. Okay. Now that I have found a1, I don't need a1 anymore. I'll differentiate one more time and get rid of a1, right? So differentiate one more time to get rid of a1. So when I do that, n into n minus 1 into 1 plus x power n minus 2 is 2a2 plus 3 into 2a3 into x n into n minus 1 an x power n minus 2. This is what transpires. And then put x equal to 0 again, because you are eyeing a2 and you want these terms to go into oblivion, at least for the time being, right? So put x equal to 0 one more time. If you plug in x equal to 0 one more time, then you get a2 equal to n into n minus 1 by 2, which is the same as 2 factorial, right? If you multiply numerator denominator with n minus 2 factorial, then what's the numerator? N factorial. What's the denominator? N minus 2 factorial by 2 factorial, which is actually NC2. If you keep doing this again and again, time and again, differentiate, put x equal to 0, differentiate, put x equal to 0, you would get A3 equal to NC3, A4 equal to NC4. In general, you'll get AR equal to NCR is what you'll get. AR equal to NCR is what you'll get. Right? Now they are determined. Now these coefficients are no longer unknown. They are very well known. Okay. Can I wipe this off? Right? So I know A0, which is NC0, A1, which is NC1, A2, which is NC2, NC3, NCR, NCN. Clear? Sounds all right? Now, so to write it in this format then, which is like NC0 plus NC1 plus NC1x plus NC2x squared plus NC3x cubed NCN x power n is what we get, right? Which is actually summation NCR x power r equal to 0 all the way to n. So sometimes they will give you an expression of this kind, either direct or cryptic. If you encounter summation NCR x power r runs from 0 all the way to n, close your eyes and then open them and write that as 1 plus x to power n. This will right away turn out to be 1 plus x power n. Okay, makes sense. And a property that we figured out, it's also customary to write this NCR as simply CR, just to save time, space, energy and resource, right? We might as well write NCR as simply CR. CR would mean it's actually NCR, right? So we would rather say 1 plus x power n is C0 plus C1x plus C2x squared plus C3x cubed plus Cnx power n, where these CRs are referred to as the binomial coefficients. They are referred to as the binomial coefficients. And a property that we've already figured out, obtained by plugging in x equal to 1 on both sides, C0 plus C1 plus C2 plus C3 plus Cn will be 2 to the power n. right? Hmm? So one of the properties that we obtained was C naught plus C1 plus C2 plus Cn is 2 to the power n. Also C naught plus C2 plus C4 will be equal to C1 plus C3 plus C5. Each will be equal to 2 to the power n minus 1. Right? Now, one noteworthy fact here is in the expansion of this, how many terms have appeared? How many dissimilar terms have appeared? N plus 1 dissimilar terms have appeared, right? Starting from x power 0 all the way to x power n, there is occurrence of n plus 1 dissimilar terms. So the number of terms in the expansion of this is n plus 1. Those are the number of dissimilar terms that appear in the expansion of this. One more than this. Now, this form of representation of 1 plus x power n in terms of well-defined binomial coefficients, right? For an internal consumption, we'll call that as a processed form. Don't quote me anywhere on this. This is only for in-house consumption, right? We'll call this representation as a processed representation of binomial theorem, right? Compact, processed, good-looking representation of binomial theorem, right? But I want you to also breed familiarity with what we would internally refer to as a raw representation. Can I wipe this off? Can I wipe this off? See, when I say a raw representation, what it really means is NC0 is actually 1. So I write this as 1. Right? This is NC1, which is n. So I write that as n. NC2 is actually n into x. NC2 I write as n into n minus 1 by 2 factorial x squared. Similarly, NC3, if you expand, will turn out to be n into n minus 1 into n minus 2 by 3 factorial x cube. Similarly, n into n minus 1 into n minus 2 into n minus 3 by 4 factorial x power 4, and going on up to n plus 1 terms. One plus nx plus n into n minus 1 by 2 factorial x squared plus n into n minus 1 into n minus 2 by 3 factorial x cubed, and so on and so forth. This kind of a relatively clumsier representation we would call as a raw representation or a raw form. We'll call this raw, we'll call this processed. Alright. And the way to read this is a full binomial rhythm. This is a full binomial rhythm. In a full binomial rhythm, what we have is, this will not be given. Let's say this is given. 1 plus London into x, right? Plus London into London minus 1 by 2 factorial into x squared. Plus London into London minus 1 into London minus 2 by 3 factorial x cube. London into London minus 1, London minus 2, London minus 3 by 4 factorial x power 4, etc. And how many terms? London plus 1 terms. So the moment you have 1 plus London into x plus London into London minus 1 by 2 factorial x squared up to London plus 1 terms, then you can right away write this as 1 plus x to the power London. 1 plus x to the power London is how you want to write it. Right? Now, can I wipe this off? Now notice that this is of course summation CR x bar r equal to 0 all the way to n, giving a full binomial rhythm, right? In this case, replace x by minus x. Replace x by minus x, okay? Then you get 1 minus x to power n is c naught minus c1x plus c2x squared minus c3x cube. This is what you get, right? Which could be written as summation minus 1 to the power r CR x power r runs from 0 all the way to n. R runs from 0 all the way to n. Check this out. See, r equal to 0 will give me CR x power C0 x power 0. R equal to 1 will give me minus, which is what we need, C1 x power 1. R equal to 2 will give me plus C2 x squared. R equal to 3 will give me minus C3 x cubed, and so on and so forth. Yes or no? R equal to 0 all the way to n. Clear? Say if someone gave me summation minus 1 to the power r CR half to the power r, where r runs from 0 all the way to n. Right, this would be 1 minus half whole to the power n. Right, summation minus 1 to power r, NCR half to power r runs from 0 all the way to n would be 1 minus half to power n. Yes means all right. Clear? Yes, yes, you can. Can I wipe this off? In this, to get a little more general and generic, replace x by a. Replace x by a. Then you get 1 plus x by a whole to the power n is c naught plus c1 into x by a plus c2 into x by a whole squared plus c3 into x by a whole cubed whole to power n, right? Is it not? Multiply throughout by a to power n, right? A plus x whole to power n, which is going to be c naught a to power n plus c1 a to power n minus 1 x plus c2 a to power n minus 2 x squared plus c3 a to power n minus 3 x cubed cr a to power n minus r x power r, right, going up to cn x power n. Yes or no? Right? Which is the generalized binomial theorem, in the sense that you see the sum of the powers of a and x in each term is n. X power 0, a power n. A power n minus 1, x. Sum of the powers is n. Sum of the powers is n. right? And the number of terms would be one more than this, n plus 1. This is in summation notation represented as summation CR a to power n minus r x power r equal to 0 all the way to n. A plus x to power n is NCR, summation NCR, a to power n minus r, x power r runs from 0 all the way to n. Clear? Sounds good? Now, can I wipe this off? A plus x power n, like I told you, is a power n plus nc1 a power n minus 1. This is nc0. You might want to write that. X plus nc2 a power n minus 2 x squared ncr a power n minus r x power r up to ncn x power n. N plus 1 terms in the expansion of this. Sum of the powers of a and x always adding up to n. Clear? Now, the first term starts with nc0. The second term starts with nc1. Right? The third term, when it's nc2, then it's the third term. When it's nc3, it's the fourth term. When it's ncr, it must be the r plus 1th term. This must be the r plus 1th term. Yes or no? This is the first term that starts with nc0. Second term starting with nc1. Third term starting with nc2. The rth term, r plus 1th term starting with ncr. Right? So the r plus 1th term in this sequence, in this summation, the r plus 1th term is ncr a to power n minus r x power r. ncr a to power n minus r x power r. That's a r plus 1th term. Right? And what is it that we have? In this case, r starts from 0 all the way to n. So this a plus x power n is actually summation of t r plus 1. R runs from 0 all the way to n. R equal to 0 will give me the first term. R equal to 1 will give me the second term. R equal to 2 will give me the third term. R equal to n will give me the n plus 1th term. So the r plus 1th term is ncr a to power n minus r x power r. Clear? Now, one plus x power n, which is c naught plus c1x plus c2x squared plus c3x cube plus crx power r cnx power n. And see, in this case, once you get it in this form, it takes no rocket science to figure out that ncr is the same as ncn minus r. So you would expect nc0 to be the same as ncn, nc1 to be the same as ncn minus 1, nc2 to be the same as ncr to be the same as ncn minus r, and so on and so forth, which is what we established even when we didn't know that a0 meant nc0, a1 meant nc1, AR meant NCR even when we didn't know that. We figured out from independent considerations that A0 must be A1, AN, A1 must be AN minus 1, A2 must be AN minus 2, AR must be AN minus R, and so on and so forth, right? Now, look, let me get another result for you. Let me get this summation RCR. R runs from 0 all the way to n. Let me get this result on for you. Summation RCR, R runs from 0 all the way to n. Now, which means 0 into C0 plus 1 into C1 plus 2 into C2, 3 into C3, and so many ways of doing this. All right, many ways of doing this. Let me tell you one after the other because they would all be instructional. Okay, so the devices that I teach you towards establishing this would be devices that would be used in very many ways at very many locations, right? Now, this, for r equal to 0, it's 0. For r equal to 1, it's 1 into NC1, that is n. For r equal to 2, 2 into NC2, 2 into NC2, 3 into NC3, 4 into NC4, n into NCN, right? Clear? Let me first, to begin with, to get you some mental exercise, deal with this in a genuinely raw form. Let me convert all these entities, NC1, NC2, etc., into their raw formats, sorry, this is r equal to 1, there will be 1 into NC1, 1 into NC1, which is the same as n, but just to make sure that you know it flushes with the rest of the members, I'll choose to write like this, right? Now, in raw format, this is the processed form, in raw format, okay? And be in sync with me. This is n, 1 into NC1, 2. NC2 is actually n into n minus 1 by 2 factorial, right? Plus 3 n into n minus 1 into n minus 2 by 3 factorial, and so on and so forth. And how many terms here? N terms. See, C1 to Cn, n terms. N terms when I write it in the processed form. N terms when I write it in the processed form. Huh? Sorry? Raw form. Sorry, raw. Okay, raw form. Okay. Now what I do is, I take n common from this. Prince. 1 plus n minus 1 into 1. You allow me to do that? Then n minus 1 into n minus 2, 3 by 3 factorial will leave you with a 2 factorial here. So, n minus 1 into n minus 2 by 2 factorial. Similarly, the next term that you get would be n minus 1 into n minus 2 into n minus 3 by 3 factorial, up to how many terms? N terms. Yes or no? Hmm? Right? So far so good? Hmm? Now, can I just remove the clutter from the top? Create room here? Hey, the way I had the process raw form was as follows. 1 plus London into x plus London into London minus 1 by 2 factorial into x squared plus London into London minus 1 into London minus 2 by 3 factorial x cubed up to one term more than this, one term more than London, right? Up to n plus 1 terms would be 1 plus x to the power n, 1 plus x power London, right? 1 plus London into x plus London into London minus 1 by 2 factorial into x squared, London into London minus 1 into London minus 2 by 3 factorial x cubed up to how many terms? 1 more than London terms. Then the whole thing gives you a full binomial rhythm, which would be 1 plus x to power London is what you get, right? In verbose, this is how I want you to assimilate this idea into your own self, right? Good. Now, it's all about how you want to read it. The same thing, you want to read it now a little differently. This quantity inside the parenthesis, 1 plus London. My new London is n minus 1 is my new London. Into x. X is 1. London into London minus 1 by 2 factorial into 1 squared, which is x squared, right? London into London minus 1 into London minus 2 by 3 factorial x cubed. Similarly, you will get London into London minus 1 into London minus 2 into London minus 3 by 4 factorial 1 to power 4, and number of terms are n, which is 1 more than London. This is our London. N minus 1 is our London, yes or no? And the number of terms are n, which is 1 more than London. So it carries the binomial pulse with it. A full binomial pulse is encrypted inside this, yes or no? Right? 1 plus London into x plus London into London minus 1 by 2 factorial x squared, London into London minus 1 into London minus 2 by 3 factorial x cubed. How many terms? N terms, which is 1 more than London. The number of terms 1 more than London, good. And all of it in the binomial rhythm, right? X is 1 here, right? So this must be n into 1 plus x, which is 1 whole to power London. London is n minus 1, right? So that makes it n into 2 to power n minus 1. Yes or no? No? Yeah. 1 plus London into x, London into London minus 1 by 2 factorial x squared, London into London minus 1 into London minus 2 by 3 factorial x cubed, up to how many terms? N terms, which is 1 more than this new London. So a full binomial sequence is available. So 1 n staying out, 1 plus x, which is 1 whole to power London, which is n minus 1. So n into 2 to power n minus 1. Do you understand this? Right? Now let me do it differently now. The same thing, let's have this taken care of a little differently. All right? S, the summation that we are seeking, summation RCR r equal to 0 all the way to n. Right? This is S, which is 0 into C0 plus 1 into C1, 2 into C2, 3 into C3, n minus 1 C n minus 1, n C n. Yes or no? Let me write it with terms in the reverse order. Let me write it starting from this point and this and this and this, so on and so forth. Clear? S. Starting from the last term, n C n. N minus 1 C, n minus 1. N minus 2 C, n minus 2. N minus 3 C, n minus 3. Terms written in the reverse order, right? Add them vertically. Let me add them vertically. When I do that, then 2s C naught is the same as Cn. So I could take C naught common from these two. So it's 0 plus n C naught. Yes or no? C1 is the same as Cn minus 1. So I could take C1 common from this. Right? 1 plus n minus 1, which is n into C1. C2 is the same as Cn minus 2. So I could take C2 common from these two. So n C2. Going this way, I could take Cn common from this. C naught is the same as Cn. So n Cn. Yes or no? Right? This is like, now I take n common from this and I get C naught plus C1 plus C2 plus Cn. Yes or no? Right? But C naught plus C1 plus C2 plus Cn is what? 2 to the power n. So this is n into 2 to the power n, which means 2s is n into 2 to the power n, or s would be n into 2 to the power n minus 1. Right? Does it make sense to all of you? Right? So this is an important result. I'll tell you another way of doing this then. Summation RCR n into 2 to the power n minus 1. The first thing, we address the whole thing using the raw format. Now, using the what we would call as the method of reversals, we reverse the entries and then we added them vertically to get this. Let me tell you another way of handling the whole thing. Can I wipe this off? See, 1 plus x power n is C naught plus C1x plus C2x squared plus C3x cubed plus Cnx power n. Right? Isn't it? Differentiate both sides with respect to x. With respect to x. Then you get n into 1 plus x power n minus 1 is c1 plus 2c2x plus 3c3x squared RCR x power r minus 1 NCN x power n minus 1. Is this not what you get? Put x equal to 1 on both sides now. Put x equal to 1 on both sides now. So if you plug in x equal to 1 on both sides, then you get n into 2 to the power n minus 1 is c1 plus 2c2 plus 3c3 NCN is what you get, right? And in this, if you add 0 into c0, there would be no loss of generality, because 0 into c0 is anyways 0, so you can add a 0 here, right? So is this not summation RCR r equal to 0 all the way to n, which is n into 2 to the power n minus 1, right? Now, to make life a little more general on this front, can I wipe this off? Suppose someone gave you a summation of this kind, S, which is say A0 C0 plus A1 C1 plus A2 C2 A3 C3 AN minus 1 CN minus 1 AN CN. Suppose someone gave you something like this, right? Where in the earlier case, A0 was 0, A1 was 1, A2 was 2, A3 was 3, AR was R. Summation RCR is what we dealt with in the previous summation. Now this time we have a summation where C0, C1, C2 are NC0, NC1 as is conventional, right? Now suppose these numbers A0, A1, A2, etc. are in arithmetic progression. See, these ARs constitute an arithmetic progression. That means A0, A1, A2, AN are in AP. A0, A1, A2, etc. are in AP. Got me? Now again, what I do is I deploy the same method of reversals. I write the last term first, second last term second, and so on and so forth. So let me again deploy the method of reversals. AN CN plus, right, A1 AN minus 1 CN minus 1 AN minus 2 CN minus 2 A1 C1 A0 C0, right? And now I vertically add them, and now I vertically add the two. So I get 2s, 2 times the required summation. Now C0 is the same as Cn, so I could take C0 common. So A0 plus AN C0. C1 is the same as Cn minus 1, so I could take C1 common. Take C2 common. C2 is the same as Cn minus 2. Cn is the same as C0, so I take Cn common. Yes or no? Tell me. Sounds good? Perfect? Hey, in an arithmetic progression, The sum of terms equidistant from the beginning and end must be the same. So can I say a naught plus an must be the same as a1 plus an minus 1, must be the same as a2 plus an minus 2, must be the same as a3 plus an minus 3, must be the same as an plus a naught. Sum of terms equidistant from the beginning and end must be the same in an arithmetic progression, right? So I could take a naught plus an common from this, because all these are equal to a naught plus an, right? And within the parenthesis, then the residual entities are c naught plus c1 plus c2 plus c3 plus cn. Yes or no? Hey, but what's this? 2 to the power n. This is 2 to the power n. Clear? So this is like a naught plus an 2 to the power n, and that's twice s. So s would be half of this, isn't it? S therefore would be 2s is this. S therefore is 2 to the power n minus 1 into a naught plus an. How about this? Got me? Now, one plus x power n is what? C naught plus c1x plus c2x squared plus c3x cube plus crx power r plus cnx power n, right? Hey, by the way, do you remember this? Function raised to a certain power into the derivative of the function is going to be what? Function to power n plus 1 divided by n plus 1, right? Let me integrate both sides with respect to x. Right? 1 plus x to power n dx is c naught plus c1x plus c2x squared plus cnx power n dx. Right? This is a function raised to the power n. And what's the derivative of 1 plus x? 1, isn't it? Into the derivative of the function. So function raised to a certain power into the derivative of 1 plus x is going to be what? 1 plus x to power n plus 1 divided by n plus 1 plus a constant of integration, right? Now, when I integrate the right hand side, c naught x plus c1x square by 2 plus c2x cube by 3, isn't it? This would be c naught x plus c1x square by 2 plus c2x cube by 3 plus, you know, a constant from all of them coming, one single constant. But this constant and this constant could be clubbed together to give a consolidated constant of integration, right? So why write that many constants? Let me just say one consolidated constant k. Let me call it one consolidated constant k. Right? Now I have to know k. I have to know k. Put x equal to 0 on both sides. This is an identity. Put x equal to 0 on both sides. Then I get 1 by n plus 1 plus k equal to 0, or k equal to minus 1 by n plus 1. So I can plug in k equal to minus 1 by n plus 1 here and get another result, right? So can I just remove this from top, giving us another commonly used result. Plugging in k equal to minus 1 by n plus 1 here, I get 1 plus x to the power n plus 1 minus 1 divided by n plus 1 is c naught x plus c1 by 2 x squared c2 by 3 x cubed is what I get. Yes or no? Now, let me obtain this result without calculus, without using integration. Let me obtain this result without using integration. All right. Now, one more thing. If you didn't want to obtain a k like this, then when you integrated the whole thing, you know what you could have done is you could have said 1 plus x power n dx, integrate from 0 to 1, and right hand side also you integrate from 0 to 1, then the k will not appear. You know what I'm saying? When you integrate from 0 to 1 in a definite integral, a constant will not appear. So when you integrate from 0 to 1 both sides, then the k will not find a place. Right. Okay. You will get the same result if you integrated both sides from 0 to 1, then k has no issues with it.
So why can't we integrate it? Why is it legitimate? Why integrating?
Why can't we?
What does it mean?
No, it means I have the luxury to do whatever I want to get some useful, good looking results which I may want to use at other places. I want something like this, c naught plus c1 by 2 c2 by 3. How do I get that? When I integrate this, I can get a 2 in the denominator. When I integrate this, I can get a 3 in the denominator. Suppose I wanted something like this with my binomial coefficients, then integration is one thing I could take recourse to, isn't it? What?
Yeah.
That's what. Now, same thing, let's say want to find without integration. I want to find the value of this without taking recourse to integration. I want to find the value of this without taking recourse to integration. See, I start with this c naught x plus c1 by 2 x squared plus c2 by 3 x cubed c3 by 4 x power 4 right. Let me write this in raw format. Okay. C0 is 1. So x. C1 is n. N by 2 factorial x cubed, or just leave it as 2 right now, x squared. C2 is n into n minus 1 by 2 factorial. 2 factorial into 3 would be 3 factorial x cubed. N into n minus 1 into n minus 2 by 3 factorial. 3 factorial into 4 would be 4 factorial, right? How many terms here? N plus 1 terms. See, C0 to Cn is n plus 1 terms. Yes or no? So far, so good. Now, let me take let me take n plus 1, 1 by n plus 1 common from the whole thing. Okay. From this, let me take 1 by n plus 1 common. Clear? Then I end up getting n plus 1 into x, right? This will become n plus 1 into x. N plus 1 into x by 2 factorial x squared, right? N plus 1 into n minus 1 by 3 factorial x cubed. How many terms here? N plus 1 terms, yes or no? What do you say? Bolo. It would have been good if there was a 1 here, isn't it? Then semblance of the sequence would surface, right? Why not? If it's not there, who stops you from adding 1? So inside the parenthesis you have added 1. That means outside the parenthesis you must take care of minus 1 by n plus 1, because 1 by n plus 1 is added. You subtract 1 by n plus 1 outside the brackets, right? For equilibrium of the expression, right? Now, if I add 1, how many terms are there? N plus 2 terms inside the parenthesis, right? Right? Now, all that you need to do is to read it with love and affection. 1 plus, this is my new London, 1 plus London into x plus London into London minus 1 by 2 factorial into x squared, London into London minus 1 into London minus 2 by 3 factorial x cube. Number of terms are London plus 1, 1 more than London, n plus 2 is 1 more than London. Do you see appearance of a full binomial pulse there? Right? So that must be 1 plus x to the power London. And what's the new London? N plus 1. So this then is as good as this then going here is 1 by n plus 1, 1 plus x to the power London, n plus 1, and then we balanced it here, minus 1 by n plus 1, which is 1 plus x to the power n plus 1 minus 1 by n plus 1. Right? Yes or no? Does it make sense? Right? Okay. Now a consequence of this result. So this is another result that you have to commit to your heads. Can I wipe this off? If in this you plug in x equal to 1, if in this you plug in x equal to 1, you get c naught plus c1 by 2 plus c2 by 3 plus c3 by 4 cn by n plus 1 is 2 to the power n plus 1 minus 1 by n plus 1 is what transpires. Right? So another result which we use time and again, c naught plus c1 by 2 plus c2 by 3 c3 by 4 cn by n plus 1 is 2 to the power n plus 1 minus 1 by n plus 1. Clear? Clear? Suppose I want to find the value of C naught say C naught minus C2 by 3 or plus C2 by 3 plus C3 by C4 by 4 5 and so on and so forth. Suppose I want to find the value of this C naught plus C2 by 3 plus C4 by 5 etc. I want to find the value of this. What will I do? See, if you plug in x equal to minus 1 here, what would you get? If you plug in x equal to minus 1 there, then you get minus 1 by n plus 1 equals minus C naught plus C1 by 2 minus C2 by 3 plus C3 by 4 minus C4 by 5 and so on and so forth. This is what you get, right? Now this equation and this equation, if you subtract this with this, what would you get? 2C naught, C1 by 2 will get cancelled with C1 by 2 plus C2 by 3, 2C2 by 3 plus 2C4 by 5 and so on and so forth. If you do this minus this, right? So if I subtract, what will I get? This minus this, I end up getting twice C naught plus C2 by 3 plus C4 by 5 is what I get when I subtract, right? Didn't understand this? Oh, sorry. See, I did this minus this. So then C1 by 2 will get cancelled, C3 by 4 will get cancelled, and what's left with is C naught, 2C naught, 2C2 by 3, C4 by 5, etc. is what you're left with. And that turns out to be 2 to the power n plus 1 by n plus 1. 2 to the power n plus 1 by n plus 1 is what you're left with, isn't it? This minus this is 2 to the power n plus 1 by n plus 1 is what you're left with. How about this? Am I confusing you, or are you all in sync with me? Sync. Which means C naught plus C2 by 3, etc. is 2 to the power n divided by n plus 1. If I add it, then I'll get C1, C3, C5. Those are the terms that will then appear in the expression, right? Okay, now this was with a lot of integration and stuff. Suppose just this was given. It's not like you'll go back to the previous results and then add and subtract and do all that blah blah blah. Not going to do that, right? Let's go from first principles. Given this, let me deal with it. Let me deal with it from first principles in the raw format. First principles in this context would be raw format, right? Let me deal with this expression in the raw format and see. So it's all about, I'm just trying to get you mentally very acclimatized to this thought. All right. So far so good, right? Very good. Let me deal with this expression from first principles in the raw format. Right? C naught plus C2 by 3 plus C4 by 5 right? C naught is 1. C2 is n into n minus 1 by 2 factorial. 2 factorial means this will become 3 factorial, right? NC4 is n into n minus 1 into n minus 2 into n minus 3 by 4 factorial, right? 4 factorial into 5 would be 5 factorial. Yes or no?
Yes, sir.
Right? Now the terms are sequencing this way. Okay? Now, I take 1 by n plus 1 common from this. I take 1 by n plus 1 common from this. Then this would be like n plus 1. This would be n plus 1 into n minus 1 by 3 factorial. Right? Yes or no? Good. So far so good, right? This is 1 by n plus 1. This is n plus 1 C1. This is n plus 1 C1. Check this. This is n plus 1 C3. Come on. You didn't do it that well, whoever did it. This is n plus 1 C3. You're skeptical about this? No? N plus 1 C3? That will be n plus 1 C5. Right? And going this way? Yes or no? Now, the result that we've learnt is the following. PC1 plus PC3 plus PC5 etc. would be 2 to the power p minus 1, isn't it? That's the result that we learned. PC1 plus PC3 plus PC5 is PC0 plus PC2 plus PC4, and each will be 2 to the power p minus 1. Yes or no? Didn't we learn this result? Right? So p here is n plus 1. Right? So 2 to the power p minus 1, isn't it? This is 2 to the power n plus 1 minus 1. So this is 1 by n plus 1, 2 to the power p, which is n plus 1 minus 1, which is 2 to the power n divided by n plus 1. Right? So that's dealing with the raw format. Always, don't forget the roots. The raw format is the root, and always take proper notice of it and be mentally very intimate with the raw format. Get very mentally intimate with the raw format. Okay? Sounds fine?
Yes.
Right? Now, many applications of binomial theorem, but let me tell you, one very important application of binomial theorem is to test for divisibility. But I'll take a little detour, distract you a little bit before I get into some divisibility issues pertaining to binomial, some general divisibility issues, as in, let's say, one thing that you should feel good about is what's referred to as the remainder theorem. Remainder theorem, which means if I have a function of x, and I divide it by x minus a. A function of x and I divide it by x minus a. When I do a division, what are the two things that happen? It results in a quotient and it results in a remainder, right? Isn't it? 5 by 2, 2 is the quotient, plus 1 remainder divided by the divisor. Quotient plus remainder divided by the divisor, right? Now, if I have, this is x minus a is a polynomial of degree 1. It's a polynomial of degree 1. When you divide by a polynomial of degree 1, the remainder would be 1 degree less than the divisor. The remainder will always be 1 degree less than the divisor. That means the remainder would be of degree 0. That means will be a number. Right? So when I do this, then what happens? A quotient qx. Now, if fx is a polynomial of degree n, then the quotient would be of degree n minus 1. Right? Quotient would be of degree n minus 1 if fx is a polynomial of degree n. Right? Plus, the remainder in this case would be a number. Why? Because degree 0 divided by x minus a divided by divisor. Is this an equation or an identity? It's an identity. It's always true, right? For all values of x, it's an identity. Now, I push a x minus a on both sides. I multiply throughout by x minus a. When I do that, then fx, another identity, is x minus a into q n minus 1 x plus the remainder r. Right? Huh? It's a if this is a polynomial of degree n, then the quotient will be a polynomial of degree n minus 1. That's all, right? Put x equal to a on both sides. Put x equal to a on both sides. Then f of a would be r. Yes or no? Because this vanishes. This vanishes. That means, conclusion, if fx is divided by x minus a, the remainder of this division would always be f of a. REM is remainder. See, R is f of a. Remainder is f of a. When fx is divided by x minus a, the remainder is going to be f of a. Right? Clear? So far so good, right? So far so good. Suppose I have 2 to the power 300. 2 to the power 300 and I divide it by 7. And I want to find the remainder when 2 to the power 300 is divided by 7. When 2 to the power 300 is divided by 7, I want to find the remainder. Now what I do is, what I do is I write this as 8 to the power 100. I write this as 8 to the power 100 divided by 8 minus 1. Yes or no? Right? I want to find the remainder of this division. That means, suppose fx is x power 100 and I want to divide it by x minus 1. X power 100 I want to divide by x minus 1. Yes or no? Fx, which is x power 100, I want to divide by x minus 1. That's what I want to do. This is of the form fx, x is this, and this will be x minus 1. I want to divide. That means when the remainder, so fx is x to power 100, fx is x power 100, and a in this case is 1, x minus a. So when fx is divided by x minus a, the remainder would always be f of a. Would always be f of a, yes or no? Yes, when fx is divided by x minus a, remainder would be f of a. That means in this case f of 1. F of 1. The remainder is going to be f of 1. But what is f of 1? 1 to power 100, which is 1. So when 2 to power 300 is divided by 7, the remainder is going to be 1. In fact, you know, remainders are very beautiful entities. And they follow some very beautiful patterns, very beautiful patterns. See, even if I didn't know this, look at the pattern of remainders. When 2 to power 1 is divided by 7, what's the remainder? 2. When 2 squared is divided by 7, what's the remainder? 4. When 2 cubed is divided by 7, what's the remainder? When 2 to power 4 is divided by 7. When 2 to power 5 is divided by 7. 2 to power 6 is divided by 7. 2, 4, 1, 2, 4, 1, 2, 4, 1, 2, 4, 1. The remainders are repetitive. See how nature has produced these numbers and given them to us. Right? These remainders occur periodically. Yes or no? Yes, huh? So then, see, in this sequence, 2 to power 3 and 2 to power 300 will occur at the same place. So if 2 to power 3 is producing a remainder 1, then in the sequence realize that 2 to power 300 will occur at the same notional location. So will also produce a remainder 1. Right? Got me? Now, can I wipe this off? Now, suppose x power n minus a power n where n is even is divided by x minus a. Suppose x power n minus a power n is divided by x minus a. So what is fx? X power n minus a power n. Right? When you divide it, then the remainder, when x power n minus a power n is divided by x minus a, even or odd, does not matter, even or odd, right, is divided by x minus a. The remainder of this division must be f of a. When fx is divided by x minus a, the remainder is f of a, right? So f of a means replace x by a, which is a power n minus a power n, which is 0. That means if this is divided by this, the remainder left is 0. That means this is perfectly divisible by this. Whether n is even or odd, this would mean x power n minus a power n is always divisible by x minus a. Why? Because the remainder of this division is 0, right? What? X square minus a squared is always divisible by x minus a, x cube minus a cubed is always divisible by x minus a, and so on and so forth, right? Confused kya? No. Because the remainder is 0, this is perfectly divisible. That means x minus a must be a factor of x power n minus a power n. X minus a must be a factor of x power n minus a power n. Another result. Look at x power n plus a power n divided by x plus a. Right? X power n plus a power n when divided by x plus a. X plus a means x minus minus a. I want to find the remainder of this division. That means when fx, which is x power n plus a power n, is divided by x minus what? X minus minus a. What would the remainder be? F of minus a must be the remainder. Yes or no? The remainder must be f of minus a. F of minus a means minus a to the power n plus a to power n. And when n is odd, it's going to be 0. This is 0 when n is odd. Isn't it? Because when n is odd, it's minus 1 to power n, a power n plus a power n, it's going to be 0. But not 0 when n is even. When n is even, it's not going to be 0. Which means every time n is odd, x power n plus a power n is divisible by x plus a, is divisible by x plus a. Every time n is odd, x power n plus a power n will be divisible by x plus a. Yes or no? See, x cubed plus a cubed is divisible by x plus a, but x square plus a squared is not divisible by x plus a. X power 5 plus a power 5 will be divisible by x plus a. X power 7 plus a power 7 will be divisible by. So every time n is odd, x power n plus a power n must be divisible by x plus a. Must be divisible by x plus a if n is odd. Right? Suppose, not confused now? When fx is divided by x minus a, suppose, say the remainder of this division is L. Fa is L. When fx is divided by x minus b, say the remainder is m, which is f of b, isn't it? L must be f of a given, m must be f of b given, isn't it? Right? Now, I want to find the remainder. I want to find the remainder when fx is divided by x minus a into x minus b. I want to find the remainder when fx is divided by x minus a into x minus b. Okay. See, the remainder would always be 1 degree less than the divisor. So in this case you are dividing by a quadratic, a polynomial of degree 2, the remainder would be a polynomial of degree 1, isn't it? So when I carry out this division, then there will be a quotient. This division would give a quotient qx plus a remainder which would not be a number but would be a linear expression, which would be say rx plus s, say rx plus s divided by x minus a into x minus b. That would be the remainder. The remainder would be a degree 1, a linear expression, because you are dividing by a quadratic. If you divide it by a cubic, then the remainder would be a quadratic. The remainder would always be 1 degree less than the divisor. Always. Huh? Is this an equation or an identity? Identity. So now I am seeking r and s. Then I would know the remainder rx plus s. If I knew r and s, then I would know the new remainder rx plus s. Right? Multiply throughout by x minus a into x minus b. I want to find the values of r and s given fa equal to L and fb equal to m. In terms of L and m, I want to find r and s. Hey, put x equal to a on both sides. Then this will become fa, which is L. fa, which is L. This would be ra plus s. Putting x equal to a on both sides. Right? Put x equal to b. fb, which is m, equals rb plus s. Using these two equations, can I solve for r and s, simultaneous equations? Right? If I subtract, let's say r would be L minus m divided by a minus b would be r, and so on and so forth. Similarly, I can find s. So if I know r and s, then I know the new remainder rx plus s. Got me? Can I wipe this off? Now, I mean, I don't want to open the Pandora's box here, because this remainder theorem by itself is a matter of 10 classes. You know, I can go on and on with remainder theorem, but let me put brakes on remainder theorem and get back to binomial, right? Because we spoke of divisibility issues. Let's have our eyes set on divisibility in the domain of binomial theorem. Okay. Say I have 8 to the power 51, 8 to power 51, and I want to divide it by 49. And I want to find the remainder of this division. 8 to power 51, and I want to divide it by 49, and I want to find the remainder of this division. Right? Okay, yes. So let me write 8 in terms of 7 or 49, whatever is convenient. So 8 to power 51, can I write this as 1 plus 7 whole to power 51? Right? If I expand this binomially, then this will be 1 plus 51 C1 to 7 plus 51 C2 into 7 squared plus 51 C3 7 cubed, 51 C51 7 to the power 51? Yes or no? Now notice that terms from this point onwards are all divisible by 49. So they will leave a remainder 0. That means essentially I am looking at this divided by 49, and whatever remainder this leaves will be the required remainder. Yes or no? See, these terms are of the form 1 plus 51 C1 is 51 into 7 plus these are all multiples of 49. So this could be written as some 49k. All these things put together could be written as some 49k. Right? Now when I divide by 49, this gives me an integer, not a problem. But when I divide this by 49, see, 1 plus 51 into 7, I could write as 1 plus 49 plus 2 into 7, right, which is like 15 plus 49 into 7. Yes or no? So the whole thing then is like 15 plus 49 into 7 plus 49 into k would be some 49 times an integer I. Isn't it? Confused kya? Little bit? No? So now when I divide by 49, the remainder is 15. When I divide by 49, this whole thing, the remainder is 15. Yes or no? Confused? Yes, no? Last step or the one before that? See, when I divide this by 49, 15 plus 49i, what would I get? This will be I plus 15 by 49, isn't it? So then what's the remainder? 15, isn't it? Because the rest of the thing is divisible by 49, this one then is the residue. Isn't it? Right? Very good. Could do that. Perfect. No issues. Suppose this expression 2 to the power 3n plus 3 minus 7n minus 8. I want to see if it's divisible by 49. I want to see if it's divisible by 49. 2 to the power 3n plus 3 minus 7n minus 8. I want to check if it's divisible by 49. Clear? Now this could be 2 cubed is 8 into 8 to the power n minus 7n minus 8. This is 8. 1 plus 7 to the power n minus 7n minus 8. Right? This is 8. Now I expand this binomially. 1 plus nc1 7 plus nc2 7 squared, nc3 7 cubed, ncn 7 to the power n minus 7n minus 8. Yes or no? Now when I divide it, now what would happen? These terms anyways are not an issue. They'll be divisible by 49, 7 squared onwards, right? And then you have this 8 getting cancelled with this 8, right? and this would be 7n into 8, right, minus 7n. 7n into 8 minus 7n is 49n, isn't it? 56 minus 7, 49n, right? So the whole thing, this 8 will get cancelled with that 8, so 49n plus, all others are multiples of 49, so like 49k. So this is perfectly divisible by 49. This is perfectly divisible by 49. No? Did you understand the expansion of this? 8 into 1 minus 8 getting cancelled. NC1 is n. 7n into 8, 56 minus 7, 49. This whole thing is divisible by 49. Right? Suppose clear? I have 17 to the power 10. And I want to find the last 2 digits of this, the last 3 digits of this. The last 2 digits of this, 17 to power 10, 17 into 17 into 17, and the last 3 digits of this. All right. Yes, 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 please ask. Ask, bhai, ask, no problem. Huh? Yes, please. Oh, yes. Here you go, that's the answer. Use the calculator. Please do that right now. Take your calculator out, see if you can find 17 to the power 10 and then divide it and see what it gives you as the last 3 digits, the last 2 digits. Way to go. Hey, by the way, if I expand, say, x minus a to power n, this is like saying, just one thing, this is as if it's x plus minus a whole to power n. This would be nc0 x to power n plus nc1 x to power n minus 1 minus a plus nc2 x to power n minus 2 minus a whole square plus nc3 x to power n minus 3 minus a whole cubed, and so on and so forth. That's binomial theorem. That's what binomial theorem is. So this is like nc0 x power n plus minus nc1 x power n minus 1 a plus nc2 x power n minus 2 a squared. Realize that the terms are alternating in sign, a cubed and so on and so forth, right? You understand this? Okay. Now 17 to the power 10. Calculators. (289) to power 5. Yes or no? 17 squared is 289, is it? 289? 289 to power 5? Purohit ji, what are you thinking? Okay. What was your thought? Achha. Okay. Yeah, you could. I mean, it's a plain canvas. Paint your own picture the way you want to. Yes or no? Nahi? Why not? Yaar, I like it, yaar. Please let me take it. तो तुम गुस्सा क्यों हो रहे हो? Okay. So then this is 290 to power 5 the first term, 5c0, then the terms will alternate. 5c1, 290 to power 4 into 1 plus 5c2, 290 whole cubed, 5c3, 290 squared, (290) minus 5c5. Yes or no? Right? Now realize 5c3 is what? 10. 5c3 is 10. So you will have a 10 cubed here. Yes or no?
Yes, sir.
You will also have a 10 cubed here.
Yes, sir.
You will also have a 10 cubed here, a 10 cubed here. Yes or no? So when you divide by 10 cubed, 1000. Hey, when you divide by 10, you get the units place. When you divide by 10 squared, you get the units and the tens place. When you divide by 10 cubed, you get the units, tens and the hundreds place. Isn't it? That's what you need, isn't it?
Yes, sir.
So you want to divide by 10 cubed and find the remainder, isn't it? That will give you the last 3 digits. If you divide by 10, then the remainder will be the units place. If you divide by 10 squared, then the remainder would be the units and the tens place. 10 cube, units, tens, hundreds place. Last 3 digits and so on and so forth. So to get the last 3 digits, what would you do? You will divide by 10 cubed. Now when you divide by 10 cubed, what is this? This is 1450 minus 1. The last two, which is 1449. I hope I am right. 1450 minus 1. 1449, these last two terms add up to 14. Isn't it? 49. And the rest are multiples of 10 cubed. Right? So then the whole expression is like a 10 cubed into an integer I. This one up to this point, this is 10. 10 squared, 10 cubed. You'll have 10 cubed in each of the terms. So 10 cubed into I and then plus 1449. Now when you divide by 10 cubed, the remainder would be what? 1449 when you divide by I'm sorry, what you could further do is you could write this as 10 cubed plus 449. Isn't it? You could write this as 10 cubed plus 449. So now when you divide by 10 cubed, what's the remainder? 449. So last 3 digits would be? When you divide by 10 squared, the remainder would be 49. Last 3 digits are 449. Last 2 digits are 49. The last digit is 9, which was not an issue. Isn't it? The last 3 digits of this number 17 to power 10 would be 1 that is obtained on dividing by 1000. When you divide this by 1000, you get the last 3 digits, which is 449. How about it? Right?
So is there any method to calculate 17 to the power 10 without so much calculation?
No, not. Sorry. Without calculations, you want to calculate 17 to the power 10, then why on earth are they going to come up with calculators? They wasted so much of their energies and resource. No, I mean, you could do a logarithm, take log and anti-log, right? You want to go to Bombay without going to Bombay. Okay. Now, here's another one. Divisibility. Divisibility is a lot of fun. Huh? What? Yeah? How? No, one of the things, not all of them. That 2 to the power 3n plus 3, that one, but not all of them.
But am I only just
No, if there is something to induct on, then you will use induction. But how do you say 17 to power 10 with induction? Okay, take this. Are you ready with your calculators? Then be ready with your calculators. Plus 2222 to power 5555. Your calculator. Plus 5555 to power 2222. Okay. Okay, now divide that by 7. Find the remainder when I divide this by 7. If you actually forget the calculator, you take the most sophisticated computer on the planet, it will take, to calculate this number, it will take a couple of days or more. That's the time it will take to calculate this number. And then you divide by 7. Okay, now that may not take very long. But then, and it would require a code to do this calculation. You can't plug in values like a robo and get an answer out of it. It will require perhaps a 20,000 lines of C code to do this calculation. Now, let's not get into the C. Okay, let's see. Way to go. So if I'm checking to find the remainder on dividing this by 7, what I do is, let me express the entities here in terms of 7 first. Right? So 2222 is actually 7 into the quotient 317, remainder 3. Yes or no? Right? 5555, when I divide by 7, then the quotient 63, 3 plus 4, 4 is the remainder. Huh? No, anyone can tell so fast. See, when I divide by 7, the quotient is 3, 1, 7 7s are 49, 3 remainder. That's what I did. Huh? Oh, okay. I say no, 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 no. Sounds good, right? Now, your attention please this time. Yes. So what I do is, this is 7 into 317 plus 3 whole to power 5555 plus this is 7 into 793 plus 4 whole to power 2222. Right? Realize that except for the last term, which is 3 to power 5555, everything else will contain a 7. NC0 into this to power 5555 plus NC1 this to power 5554. Right? All terms will contain 7 except the last term. What's the last term? 3 to power 5555. That's the only one that will not contain 7. So this is like all of the terms that contain 7, let me call them 7k1 plus 3 to power 5555. When you expand this binomially, what would you get? This to the power this plus this C1, NC1 this to power 5554, this NC2, this to power 5553, and so on and so forth. So all terms except the last term would be 3 to power 5555, all of them will contain 7 in this expansion. Similarly, look at this. Except for the last term, all of the terms will contain 7. So when they are consolidated together, they would be like a 7k2 plus 4 to power 2222. Right? So this is like 7k1 plus 7k2 is like a 7k together divisible by 7. Right? Plus. Now 3 to power 5. 243, isn't it? 3 to power 5 is 243. So this is 243 to the power 1111. 3 to power 5 whole to power 1111. 3 to power 5 is 243. Right? Plus 16 to the power 1111. A result which I told you, if n is odd, x power n plus a power n must be divisible by x plus a. Did I tell you this? Right? So x to the power n plus a to the power n, this must be divisible by x plus a. 243 plus 16, which is 249, 259, which is 7 into 37. Yes or no? That means these two together are divisible by 7. These two, this is divisible by 7. Therefore, this number, so sweet and small, is divisible by 7 indeed. Right? Got me? Huh? How will that help? Then again you will expand. Could do that. But right? See, again, there are times you would have to deal with something like C0 squared plus C1 squared plus C2 squared plus C3 squared plus Cn squared. Alright. C0 squared plus C1 squared plus C2 squared plus C3 squared plus Cn squared. In all these cases, first thing that you do is close your eyes, open them and write 1 plus x power n. Write the expansion of 1 plus x power n. You could have written this. See, one thing, 1 plus x power t, coefficient of x power r in the expansion would be TCR, right? Do you all understand this? Coefficient of x power r in the expansion of 1 plus x power t is going to be TCR, right?
This means the total sum of coefficients of any binomial expression will be independent of x.
No, this is coefficient of x power r. That means there is a term x power r. It comes married to a term TCR. That's the kind of term. That's the coefficients also are coefficients are different from these always, isn't it? 1 plus x whole squared is 1 plus 2x plus x squared. Coefficient of x power 0 is 1. Coefficient of x power 1 is 2. Coefficient of x square is 1. Why should that contain x, right? Coefficient of x power r in the expansion of 1 plus x power t would be TCR always, right? Now I could have also expanded this. This is in ascending powers of x. This is in ascending powers of x. I could have written the whole thing in descending powers of x. That means I could have written this as x plus 1 to power n, and that will be like c naught x power n plus c1 x power n minus 1 plus c2 x power n minus 2 plus cn in descending powers of x. Right? Bolo. Now, I multiply these two out. When I multiply these two out, I get 1 plus x power 2n is what I get when I multiply these two out. And that must be equal to c naught plus c1x plus c2x squared plus c3x cube x power n into c naught x power n plus c1x power n minus 1 c2x power n minus 2 cn. Right? Could this be done? This into this into this. Right? This is identical to this. Coefficient of x power London here will be equal to coefficient of x power London there, because all that I have generated is an identity of two polynomials. Right? Now I have to devise a way to get c naught squared, c1 squared, c2 squared, c3 squared, etc. Right? Check this out. If I multiply this with this, what do I get? C naught squared x power n. If I multiply this with this, what do I get? C1 squared x power n. If I multiply this with this, what do I get? C2 squared x power n. Yes or no? Which means the coefficient of x power n on the right hand side, this is like c naught squared plus c1 squared plus c2 squared plus cn squared, must be the coefficient of x power n on the right hand side. Will you buy this argument from me?
Yes, sir.
The coefficient of x power n on the right hand side can be obtained. This is the only way you can obtain the coefficient of x power n, isn't it? This into this, which will give me c naught squared into x power n. Right? Nahin. This into this will give me c1 squared into x power n. This into this would give me c2 squared into x power n. Right? So the x power n terms on the right hand side, just the x power n terms on the right hand side would be of the form c naught squared plus c1 squared plus c2 squared plus cn squared x power n. So what's the coefficient of x power n on the right hand side? C naught squared plus c1 squared plus c2 squared plus cn squared. That's the coefficient of x power n on the right hand side, which is this required sum s. The required sum s is the coefficient of x power n on the right hand side. Has this registered in you? Right? So s, the required sum, is coefficient of x power n on the right hand side, that is c naught squared plus c1 squared plus c2 squared, and this must be coefficient of x power n on the left hand side, must be the same as coefficient of x power n in 1 plus x power 2n. Right? Right? Hey, I told you coefficient of x power r in 1 plus x power t is going to be what? TCR? Coefficient of x power r here is going to be TCR. Coefficient of x power n here is going to be 2ncn. Right? Coefficient of x power n here is going to be 2ncn. Coefficient of x bar r here is going to be 2nc r. Did you understand that s is the coefficient of x bar n on the right hand side, and that must be the same as coefficient of x bar n on the left hand side? Huh? What is the coefficient of x bar r here? Coefficient of x bar r here is going to be 2ncr, isn't it? So coefficient of x bar n is going to be what? 2ncn. See, if I expand 1 plus x bar to n, it's going to be 2nc0 plus 2nc1x plus 2nc2 x squared plus 2nc3 x cubed 2ncn x bar n 2nc2n x bar 2n, isn't it? Coefficient of x bar r is 2ncr. Coefficient of x bar r is 2ncr. Coefficient of x bar n 2ncn. This is again a standard result. C naught squared plus C1 squared plus C2 squared plus Cn squared is 2ncn, which is like 2n factorial by n factorial whole square.